This is the second lecture in Quantum Physics 2 dealing with particle physics. In this lecture, we're going to focus on the properties and combinations of quarks to make mesons and baryons and leptons. Last class, we talked about the list of fundamental particles, which include the 6 quarks and their antiquarks, and 6 leptons and antileptons, and the 4 force-carrying particles, plus the Higgs boson. This time around, we're going to focus on the properties of the quarks and the leptons and how they might combine and some of the limitations on those particles. Among the tools that are available to us to understand the relationships between particles and how they link together to yield fundamental particles and fundamental forces are things like, for example, the lifetime for a reaction to occur. And what we now know, based upon observation and then testing the ideas, is that with respect to nuclear reactions, that a decay which occurs very rapidly, for example, is most likely due to the strong force. That is, that a very strong interaction can lead to a rapid decay. If a particle is created, it can decay very rapidly. That if the weak force is involved in a particle decay, then that decay time is going to be much, much longer. We're seeing here of order 10 orders of magnitude longer lifetime for the weak force. The electromagnetic force on the scale of intranucleon interactions is intermediate between the weak force and the strong force, and it turns out that the time scale for decays that involve electromagnetic interactions are somewhere in between these two, 10 to the minus 14 to 10 to the minus 20 seconds. And what we believe, basically we're in a situation where we have not observed decays due to gravitational interactions, is that gravity could, in principle, lead to decays. And what we know experimentally is that, since none have been observed, that gravitationally induced decays must have extremely long lifetimes. So once again, that scales, we expect, with respect to the strength of the interaction on the nuclear scale. We identify with these interaction timescales and decay times forces that we call strong, weak, electromagnetic, and gravitational force. And in a few cases, we've been able to identify particles that act as force carriers between nucleons. And later on, in a little bit, we're going to talk about quarks. So this is part of our language here. The strong force, we say, is carried by the gluon, and it's actually a force that is carried between two quarks. We'll talk in a little bit about how the strong force between two quarks can give rise to the strong force between nucleons. The electromagnetic force, we know, is carried by the photon. Of this group here, the photon is one of the few particles that has been directly observed. In fact, we can observe it by seeing it with our eyes. The symbol is a gamma. All right, symbol for the gluon is a G. And from their interactions, we can learn something about the properties of these particles. The gluon and the photon appear, well, the photon for sure, actually, have no mass associated with them. They both have spin 1, and neither has a charge, electric charge. The weak force is carried by bosons, and these bosons, the W and the Z, have actually have mass, and that mass can limit the range of the force. The W's have charge, the Z0 does not have charge, and they both have spin 1. W's and Z's are involved in weak force interactions that involve different changes in what we'll come to know as the flavor of quarks. And then there's the gravitational force, and it is posited that gravitational force is carried by an intermediate particle called the graviton. Gravitons have not been observed. Gluons have not been directly observed, but there's evidence for them. We don't have direct evidence for the graviton, but it's proposed to have zero charge, it's proposed to have spin 2, and it's proposed to have rest energy of 0, which is what would give rise to the 1 over r squared range of the force. So that's some of the language that we're going to be using as we go along. With respect to language again, I just have a quick slide here that summarizes some of the words that we've been using. The word boson means to us a particle of integer spin. It might have mass, it might have no mass, but bosons have integer spin, and as a result obey certain rules, Bose-Einstein statistics for example, with respect to occupation of states. Fermions, we've learned electrons are fermions, but also protons and neutrons are fermions, are particles with half integer spin. There are particles that have spin which is not 1/2 but might be 3/2 or 5/2. The word hadron refers to any particle which is made up of strongly interacting quarks. Originally hadrons were thought to be fundamental particles, but it turns out that they are composite, that they are made up of quarks. So nucleons are hadrons. The quark, which is the fundamental constituent of strongly interacting particles, quarks are fermions, so they can fit into various categories here. Gluon, we just talked about. Mesons, we're about to talk about, are quark-antiquark pairs. Baryons are 3-quark particles, and they're now believed to exist baryons with more than 3 quarks, so baryon would be more than 2 quarks. Leptons are fundamental fermions that we'll talk about. These are fundamental particles, the 6 fundamental leptons. And then there are a few other things here that I've got named. The photon is fundamental. Pion and kaon are just happen to be particles made up of quarks, and they were among the earlier particles discovered that led to our understanding of the symmetries and relationships between quarks. We have one more word that I want to refer to here, which is called flavor. And flavor is sort of a weird thing. It is a term that's used to characterize the unique nature of each of the fundamental particles. Basically, flavor corresponds to the name that we give a particular particle. So, amongst leptons, there is an electron, a muon, and a tau. Because these are distinct particles, to the best of our ability to measure so far at least, distinct particles, and they are fundamental particles, meaning they're not made up of any other particles. These particles are called, each one of them is given a flavor. Electron is one flavor, muon is one flavor, tau is another flavor. And transitions between particles of different flavors are extremely unusual and involve typically weak interactions. Quarks. We have 6 quarks, and each of the quarks is characterized, is basically a flavor. There's upness and downness, the flavor. The other name to up and down is a word that's called isospin. And it's not an actual spin. It doesn't have a magnetic moment, but in many ways, statistically, isospin behaves like spin. So we give it numbers of -1/2 and +1/2. Protons and neutrons are considered to be 2 particles that differ only in their isospin. Topness and bottomness, so the top quark and the bottom quark. Sometimes topness is called truth and bottomness is called beauty, charm, and strangeness. And I mentioned the lepton flavors. So first, we're going to talk about quarks. Quarks are elementary particles. They have, by elementary, means that we have no evidence that they're made up of anything else. They are fractional charge they have spin 1/2. Oddly, they have fractional charge, that is, that they have a charge of 1/3 or 2/3 of the fundamental charge, but they can only combine in ways that make integer charges. And quarks can interact by strong force, electromagnetic force, weak force, and gravitational forces. So quarks can interact via all of the forces. How do we come up with quarks? Well, smart people is one thing. What has been observed is when particles are collided with one another, we look for energetic resonances in the cross-section. We can identify, here's some sort of resonance that is associated with a particular energy, and it might be associated with a particular angular momentum and spin, for example. So we look at all those properties together. We look at the overall behavior, the charge of the particles that are produced, the mass of the particles that are produced, and how they decay, for example, and categorize them. And Gell-Mann looked at the set of particles that were known in around 1960 and said, there's a pattern here that seems to be consistent with group theory, actually. So he was looking at mathematics and particles, and he looked at the formal relationship and came up with a pattern that looks like this. On this axis here, we have the charge of the particles that has been observed. On this axis here, we have another quality of the particles that had been observed that was related to the decay statistics, and we'll talk about that in a little bit, which is called strangeness. He looked at the particles that had been observed, the masses of the particles that had been observed, and the charges, and the decay speeds, and what they decay into, and came up with a pattern that has this symmetry to it, this 6-fold symmetry to it. And based upon that, he proposed that maybe these particles are made up of two of three other types of particles. These particles, he proposed, were made up of up quarks, down quarks, and strange quarks. These are called the conventional mesons, and they are quark-antiquark pairs. Quark-antiquark pairs, because of the fact of the half-integer spin of the quarks, are bosons. They are all unstable, that is, they decay into other things. And depending upon their strangeness, they can have weak, strong, and electromagnetic interactions. They can have net charge, as you see here. And because mesons are composite particles, they can have spin and angular momentum. And we can form particles, basically resonances for a given particle type by changing the angular momentum of the particle. And that will lead to a different energetic resonance that would be observed. So we look at all of that and conclude that we have this fundamental set of quark-antiquark pairs made up of up, down, and strange. Of course, there were 6 quarks in the table that I just showed you. So that suggests that there are a lot more particles and that this was just the beginning of the observation of the symmetries. Gell-Mann came up with this initially, and that led to people thinking about symmetries and group theory. And then someone said, well, gee, you know, if there happened to be 4 quarks, what pattern would we see? And then the race was off looking for the additional quarks and looking for the resonances, that is, new particles that would result from those additional quarks. Another set of particles that led to the understanding of the makeup of nucleons, right, was a set of particles that are composed, now we believe, of 3 quark pairs. On one axis here, we've got strangeness. On another axis, we've got isospin. And another axis, we've got charge. And we put all that together and we end up with a set of symmetries. You see here that we've got the neutron and the proton, which differ in charge. So there's the charge axis. And they differ in isospin, but they have 0 strangeness, for example. So baryons are, now we're going to say, and we'll use it later on, are particles that have baryon number of 1. Because they're made up of 3 quarks, they must be fermions. And they interact via strong, weak, electromagnetic, and gravitational interactions. Because they have mass, they interact via all 4 of these interactions. But for decays and lifetimes and transformations, it might turn out that the strong interaction is dominant, you know, that it is involved in the decay. And sometimes the strong interaction is not involved in the decay, and then the weak force will, or electromagnetic force, will dominate and control the lifetime of the particles. So once again, it's observation of the symmetries. You know, neutron and proton are very alike in some ways and very different in others. Proton and sigma are similar in charge but differ in other measures. So along each axis we have a different measure of the particle. And by observing these patterns, Gell-Mann came up with this group theoretical approach. I mentioned flavor a few minutes ago. Normally, in the American English version, we spell flavor without the U, but this was picked up from a Wikipedia article that probably was written by a British person. What are the descriptors that we use for the flavor of a particle? There is isospin, which is frequently, sometimes, referred to as upness or downness. So that's 2 different quarks have 2 isospins. Charm, strangeness, topness, and bottomness. Right? Those are the flavors that characterize quarks. Those are the 6 independent quarks, 6 fundamental quarks. Out of these quantum numbers, we can construct other quantum numbers, and we'll come back and talk about this. Other quantum numbers include the baryon number, We talked about that for 3 quark sets. Lepton number. Lepton number actually has to pay attention to the flavor of the lepton. That is it an electron or is it a muon? Those are 2 different flavors. Isospin, electric charge. Don't remember what X charge is. And then combinations of these quantum numbers. There's one called hypercharge, which includes the baryon number, the strangeness, the charm, beauty, and truth, or topness, rather. And weak hypercharge, which I'm not going to spend any time on right now. But I just wanted to include this table and give you a reference to the Wikipedia article. Here are some properties of what are called first generation quarks. The properties of these were the first that were observed, and resonances related to these quarks were the first observed. And that's in large part because the energy associated with creating quark-antiquark pairs, that is, creating a meson, for example, is relatively low for up and down, and in a little bit momentarily we'll talk about strange quarks. So we can't actually measure the mass of a quark because we have not viewed it independently, but we can look at mass differences between composite particles that have similar interactions between their quarks, similar binding energies. So the mass of the up quark is inferred to be about 2.4 million electron volts, the down quark to be about 4.8. So these are not much more massive than protons and neutrons. And you might ask, wait a minute, how could the actually, I've got this wrong. They're not very massive at all, and the protons and neutrons that make them up, of which they are made, are much more massive, and so there is a little bit of a problem here. But neutrons and protons are actually made up of the quarks plus all of the things that tie quarks together, gluons and such. So it's not so crazy. So when we look at the properties of the particles that are made up of quarks, then we find that quarks have fractional charge. The up and down quarks have fractional charge. They can only combine in ways that make integer charge. They have fractional baryon number. They can only combine in ways that make integer baryon number. And in a few minutes, we're going to talk about the parity of fundamental particles. The parity of the up and down quark are defined to be +1. Yeah, good enough. Let's move on. So we can now look at the patterns of putting quarks together in order to make the observable particles. A lot of the quantum numbers that we observe of the hadrons, that is the baryon quantum number, charge, spin, isospin, strangeness, are actually just the sum of the constituent parts, the quarks, right? Angular momentum and parity are properties of the composite particles and depend upon the space wave function. So the angular momentum of the combination of quarks can become important. Right? So here, meson with a quark-antiquark, spin anti-aligned, has spin 0. The space state with angular momentum equal to 0 then has total angular momentum equal to 0. But we can combine quark-antiquarks in different ways with both spin in the same direction, so that it has a total spin of 1. And we could also look at space states that have larger angular momenta, because these two particles are just bound to one another and can have angular momentum. And then we'll find a number of other energetic resonances with different energies. So what can we do with quarks? So let's take a look first at taking two up and down quarks and their antiquarks and put them together. So I could put together a down quark and an anti-up quark, just for example. All right. So this is a combination of a quark and an antiquark, but they don't have to be quark-antiquark pair necessarily. They have isospin, charge, angular momentum, and projection of the isospin onto the z-axis. So we have not talked about this, and we're not going to talk further about it. But this combination of down and anti-up quark yields the pi minus particle. If I take the anti-particles of this and take an up anti-down quark, then I produce a pi plus particle. And another combination of up, anti-up, down, anti-down, so the same set of particles here combined can yield the pi naught when we have zero angular momentum. If I take the same set of particles here and now permit them to have angular momentum, then I end up with another particle. So another observed resonance, let's put it that way. And because we can allow combinations, composite particles to have angular momentum, internal angular momentum, we have a lot of different energy resonances associated with a very simple quark-antiquark pair. So here's sort of a summary, not put together strictly, all right? This is just to give you an idea of our quarks and how we can put those quarks together to make some particles. There is a group of particles, I think I'm probably going to talk about this next, but I'll say it now, which are composed only of pairs of quarks. For example, up, anti-down, up, anti-up, combinations like that are called mesons. And because they've only got two quarks and all the mass associated with the associated gluons, right, these particles tend to be relatively light, intermediate between the mass of the electron and the mass of the neutron and the proton. And as a result, they were called mesons because they were intermediate mass in the middle. And baryons, first particles observed were the proton and neutron, were considered to be heavy particles. So baryon is sort of an etymological reminder of heavy. So middleweight, heavyweight from the Greek. And baryons are made up of 3 quark sets. So we've got a bunch here, but you can see we can go back now and take a look at anti-quark combinations, and there are going to be a lot of possible particles that we could just make, for example, out of the 3 quarks, which are the up, down, and strange. And you can see why these were the first found, because the up quark is quite light, the down quark is quite light. So that means that we can create quark-antiquark pairs, and the energy associated with making those pairs might not be huge. The strange quark is quite a bit more massive, but still easily achieved using old-fashioned accelerators up into the 1960s and 70s. In order to observe the other quarks, now you can see that these are getting fairly massive, more massive than the proton, but don't forget we've got to have a gluon cloud that has a lot more mass to it. And we're going to have to form anti-charm pairs, for example, in order to observe these particles. So this one, you have to have quite a bit more energy in your accelerator, and you can see that the top quark is very massive and required quite a significant advance in accelerators in order to be able to observe the top quark, which wasn't observed for a good 25 years after the observation, the inference rather, of the up and the down from the particles that were formed out of those particles. By the way, I had mentioned earlier in this course that most of the matter that we see around us, that we can see around us, is composed of up and down quarks and electrons. And that's about it. Those three particles compose most of the interactions and observations on the things that we can observe with our eyes and through observations of gravitational acceleration, for example. And the only one of these that we can observe directly is actually the photon. So without specialized instrumentation in mathematics, we would be left with up-down photon, electron. So we've introduced the quarks to a certain extent. I'm going to be sharing tables with you in a little bit, and then we'll work our way through the interpretation of data in tables. But the second important class of particles are the leptons. Leptons are elementary, that is, we have no evidence that they're made of anything smaller. They are spin 1/2, so they're fermions. They interact via electromagnetic, weak, and gravitational forces, but not the strong force. So leptons don't interact via strong force. So if they're going to decay, they can only decay by these much longer lifetime processes. Here's a table of the properties of leptons. Electrons, to the best of our knowledge, are stable particles. They don't decay into anything else. Their electron lepton number is 1, and they have a mass of 0.511 MeV over c squared, a charge of -1. The anti-electron is called a positron. It is also stable. It has a electron lepton number of -1, same mass as the electron, and a charge of +1. And when electrons and positrons combine, they can annihilate one another, releasing 2 gamma rays. Associated with the lepton and having the same electron lepton number is the electron neutrino. And the existence of the neutrino was inferred from observations of the energies of particles being emitted from beta decays, nuclei that were decaying, and the fact that the electrons weren't carrying off enough energy. And then it took several years after the proposition that neutrinos existed for them to actually be directly observed. They only interact with matter via the weak force and gravitational force, but their mass is so small that there's no observable gravitational effect, unless it turns out that there are a lot more neutrinos around than we thought. They are one of the particles that is proposed to be the source of dark mass. So electron neutrinos. Positrons, electron antineutrino associated with a positron. And in all interactions, the lepton number must be conserved. Second neutrino is the muon. It's got a much larger mass, 105.7 mega electron volts over c squared. It's got a charge, so it's actually easy to observe. And its lepton number is 1 muon lepton number. So muons and electrons both have lepton number of 1, but their flavor is different. They are fundamentally different particles. And then all the associated particles to deal with the muon, including a muon neutrino. And it is thought that in reactions that require the emission, for example, or creation of an electron, that an electron antineutrino is the fundamental particle that is emitted in that process, but that the electron, muon, and tau neutrinos are actually composed of mass eigenstate neutrinos that don't transform into one another. I'll talk about that later on. So it has been discovered that neutrinos can transform from one flavor to another, and I'll talk about that later. The tau is a very massive particle, about twice the mass of a proton, and as a result wasn't discovered until quite late. I'm going to be sharing with you a resource that I put together as far, for your reference during this course, but it can be useful later on. The resource is called Some Properties of Some Particles, and it's just a big table that includes some properties, the important properties from my perspective, of particles that are commonly referred to. And we'll be working through some of the information in this table so that you get used to it. This table will be posted in both the activity and in the lecture section of LMS. And what we're going to do as a little bit of an activity, just to break things up during class, is to work through a really sort of fun, to me at least, poster that was created by Sean Carroll. And the poster is called What Particle Are You? And you work through a series of questions and make some conclusions about what a particle, where a particle falls in the zoo of particles that can be observed. And I think that it'd be probably worthwhile for me if you all work through some examples of particles to make sure that Sean Carroll's chart, What Particle Are You?, and my table, Properties of Some Particles, are consistent with each other. 4 particles that I know they're consistent on are the kaon, the proton, the delta plus, and the photon. So it'd be sort of interesting to go through Sean Carroll's chart to ascertain that with the properties that I've got in my table, you come to the same conclusion, and then try a few others just to see whether the chart and the table are consistent with each other. If you find an inconsistency, let me know, and I'll probably end up changing a number. So here is Sean Carroll's chart, at least, and it consists of a bunch of questions that you ask about the particle that you're looking at, the thing that you're looking at. So an example, I'll go through, and no, I won't go through, because it's not that complex. I'll start here, right? And ask the question of the thing that you're looking at, how many smaller particles is it made of, right? So is this thing that you're looking at, made up of, let's say, 20 electrons, 20 protons, 20 neutrons, which are all made of quarks, right? In which case you'd answer that question many, and then you would look at those numbers and you come away and say, hey, that sounds like potassium. I think that potassium isn't 20, 20, 20, but close enough. That sounds like potassium, and that's an atom, all right? When you talk about fundamental particles, you ask, do these fundamental particles sort of have to be apart from one another in different states, or can they pile onto the same space? If they can pile on their bosons, for example. So there are a lot of choices along the trees, and you can start off and just ask what are the properties of the particle that we're looking at, work through, and decide what type of particle this is. And perhaps the most important thing is in here, somewhere around here, there's a point where it says, you've made it to the point where you found something that we don't know about. So you're going to have to search through here and find out where that is, where you have succeeded in finding something completely different. So I talked about one additional quantum number. We have talked about it before, and we've learned about parity. So parity is a property of the space wave function. That's what we have studied it as, right? Initially, but there's a little bit more to it. So the parity of a wave function tells us whether when we switch the coordinates x to minus x, y to minus y, z to minus z, does the sign of the wave function change? And if the sign changes, then it's negative parity. And if it doesn't change, it's even parity. So I'm sorry, odd even parity. It turns out that we can also actually label fundamental particles as having intrinsic parity. And more than just fundamental particles. So in the tables that I was showing you, there was a column for parity, and the parity of quarks was listed. Intrinsic parity for quarks is defined to be +1, and it turns out that nucleons then, therefore, will also have intrinsic parity of +1. The parity of a pair of particles, right, is written as the parity of particle A times the parity of particle B times -1 to the angular momentum. So this term here is what we already knew. The parity is a property of the space wave function. But here now we have the parity of the particles that are included in making up a composite particle. Parity is +1 when the total wave function is even under particle exchange, and -1 for odd. Parity was thought to be fully conserved in all interactions, but was found through some very clever experiments to not be conserved in weak force interactions. So parity, let's say I have two particles that collide with one another, and we know the parity of the particles coming in, we know the angular momentum. That parity is going to be conserved in strong and electromagnetic force interactions, but it is not conserved in weak force interactions. We're going to talk in the next class about actual interactions and decays and lifetimes, but you have some idea already that you can fairly easily characterize the interactions that are important just based upon a little bit of information. You can predict whether and how fast a decay can occur based upon conservation laws and based upon the characteristic times for the decays to occur. We're going to start working through in the class the particle physics worksheet, and then you're going to finish this worksheet, which has decays and interactions on it. You're asking what's possible, what particles can exist, what decays can occur, based upon these conservation laws. So you need some conservation laws, and we'll be talking about that. And here they are. Conservation laws and reactions include total energy, total momentum, angular momentum conserved. Now, later on, perhaps after the last exam in this course, I'm going to, the final exam in the course, I'm going to discuss a bit about invariant quantities and conservation laws a little bit more deeply than we did when we were talking about special relativity, but it is all related. And I'll just comment here that when you have a quantity like translational invariance, so if when you change the position of a reaction and nothing else changes in the situation, if it turns out that that leads to exactly the same set of relationships, then that's called translational invariance. And it turns out that the property of translational invariance leads to conservation of momentum. And I'll talk about others later on. I was just about to run on it, and that's not part of this lecture. Right now, I'll just say this, that we have a set of quantities that are conserved in all interactions and decays, for example, collisions, decays, and so on. Another number that appears to be, and this is experimental largely, all right, appears to be conserved in all interactions and decays is the baryon number. The third is the lepton number. And lepton number, paying attention to flavor in addition, unless we're talking about neutrinos, and we'll talk about neutrinos later on. But electrons don't just disappear. They have to, at the very least, if an electron disappears in a situation, we have to form an anti-electron neutrino. There are certain derived quantum numbers that are conserved under certain interactions, electromagnetic and strong interactions. I mentioned hypercharge, which is a baryon number, strangeness, bottomness, charm, and topness, and electric charge, which is a combination of isospin and hypercharge. And then the comment here in determining whether a particle can be observed or not. So far, and the standard model predicts that all the observable particles will have integer charge. We'll never see a free quark. But that doesn't stop us from trying. Experimentally, you try even those things that theory says shouldn't happen. And if they do, then you tell the theorists that they have to rethink things. In class, we're going to go through another worksheet, and we'll just start this worksheet, and then you'll finish it for homework.